This time it will work. So let's see, can you see my writing?
Yes, I do.
Okay, so the plan was to first cover existential quantification and its encoding via for all in data constructors. The reason I want to cover that is that if we understand how existential quantification works and how equality constraints work in GHC, we can understand how JADTs work, and understanding JADTs is very important if we want to start working with vinyl and union. So when we write a data type, let's call it A, and it has a constructor, we can write, there are two places where we can write a for all. Actually, three places, I think. Here's the first place, here's the second place, and here's the third place. And if I write something like that, data A, no, the first place is not here, but here. So if I write something like that, this means that my data type has a single type parameter A, and its data constructor will look like this. Let's call it make A. That's the Unicode syntax for all. In Haskell, you would write for all with Latin letters, but I will save some space and write it with the Unicode syntax. The constructor will have this type. And you can see here that if we write the type parameter in this position, it is reflected in the return type of the constructor. However, if I write it to the right of the equals sign, if I write data B equals for all A, make B A, then in this case, the for all, the constructor will have the same for all in the beginning, but the return type will not mention this type variable. What does this mean in practice? In practice, it means that when we take some value of type A as input to our function, we can put some constraints on its type parameter and get some knowledge about it. So let me create another page here. So on the second page of the drawing, I'm going to show you an example of that. If I write some function foo, and it's taking some type A, and returning, let's say, an integer, then we can put some constraints on this A type variable. So if, let's say, I say that we have the constraint C that gives us a function size of a int, I can here pattern match on the constructor, bring a into scope, and call this method on this a. And this, you will notice that a here is just the identity wrapper. It just stores its parameter and does nothing interesting with it. I have put a constraint on it. I have applied a function to it. But in case I take the second type B as input, there is no type parameter here, you see? So when I write the implementation of this function, maybe I bind this A, there is literally nothing I can do with the thing that I have bound, because its type is opaque to me. Okay, so the live board isn't updating. Are you sure that you are on the second page of the live board?
No, really, it's kind of updating, kind of slow. Like, I only saw you write the second foo now, without the B.
That's very bad, because I was hoping that I could... Damn it. So it seems that I am actually going to start writing code in Google Docs, as Dmitry suggested. Oh, all right. Give me a minute. Okay, so back to the code that we had. I wonder if I can disable auto completion, because it will make my letters uppercase, so not valid Haskell. Maybe if I create a table, it won't do it here. It will. Does anyone know how to disable auto capitalization in Google Docs?
No idea. Maybe you should find like a code writing service or something instead.
So I found it in settings. So use smart quotes, no, detect links, lists, automatic substitution, suggest contacts and comments, suggest action items, disable everything. Okay, so this is now like the Notepad application. I can type text into it. Amazing. I don't need a table, I think. So if we define data type like this, then if we define a data type like this, then function that accepts it as input can assume things about this type variable. So I can say that it is a string and foo make a length a. This will work. However, if I define a data type like this, then a function that takes it as input has no way to assume anything about the value that it brings into scope, the constructor. So if you define these things in GHCI and you look at their type signatures, you will see that make A has type for all A to, no, A to A, and make B is the same thing, but it doesn't have this type variable mentioned in its type signature. So the difference here is basically if the type variable is mentioned in the type signature, and this affects how we can work with it. And this is the difference between the fundamental difference between existential quantification and universal quantification in Haskell. Of course, a better way to make sense of it is to compare universal quantification to a function and existential quantification to a tuple. So when we have something that says for all a, f of a, this means that to this thing we can supply any a and it will obey. It will become f. So I can say, for instance, I have id for all a to a, and I can say id of int, and it will become id int to int. But if I have existential quantification, so I have something of type exists a, f of a, then it means that it tells me what type a it has. So the first function, the first case, the for all case is like a function because I can supply the input to it. I can say let this a become int, and it becomes int. However, in case of existential quantification, I cannot say that to the construction. I can only ask it what type a do you have, and in the data a case, what we have here is that we tell the input b, let this type variable be a string. We instantiate it to a string, and we can work with it. We can work with a string. However, b comes on its own terms. It tells us, I have some a inside of me, but I'm not going to tell you which type it is. It's just some type that I want. And when we are constructing, the same rules apply. So when I'm going to construct something of type a string, I can only use a string here. So it's make a hello, but this type checks, but make a 15. Obviously does not type check. In case of b, I can write make b hello string, will type check, and I can write make b 15 int. This will type check. So the difference here is that all right. So this is probably kind of obvious what happened here. So there's confusion happening when people start to write for all in the wrong place. So what I described above, it's basically a type variable is either reflected in the type signature or not. But what if it's reflected but in a different way? I can define data C, make C, and here I have a for all to the right of the equal sign, but it is inside of the constructor. It's a field in the make C constructor. In this case, the type of the constructor that we have is roll AA to C, and this here is a higher rank type. And this is not existential quantification anymore. This is universal quantification again, because here we have a single field in the make C constructor, and it is universally quantified with a for all, and it says, I will become the type you want. So the function foo, when it takes C as input and tries to return an int, it can take the A inside, say, let A be a string. This is basically supplying this A parameter to A, and then call length. So what we have here is 3 places where we can put for all. We can put it in the beginning of the constructor and reflect it in the type signature of the data constructor. In this case, this is universal quantification. However, if we do not reflect it in the type signature of the constructor, this is existential quantification. But if we don't reflect it in the type signature of the constructor, but it is not about the data type itself, it's only about a single field, then it's universal quantification again. And to not confuse these 3 cases, the most important intuition is of a function and a tuple. So let's take a look at these cases again, and I'm going to move on to the next point. Here we have used universal quantification, and no, where's the first foo definition? Here we have used universal quantification on A. We can say, but we supplied its value as string, so we know something about it. Here we have existentially quantified A, so it comes as a field of B itself. It's like the type is like stored in the constructor. Of course, not at runtime, but conceptually, it's something that belongs to the constructor. So we get it as input here, and here in the C case, we again have a function. We can tell that A what type to be. So it's like passing a type parameter to it. And the next point I was going to cover is equality constraints. And they work like this. Let's say you have a function int to bool, but I want to write it in a really obscure way. So I will say that I have a function from A to B and put 2 constraints, A equals int, B equals bool. And this is exactly the same type signature. The constraints to the left of the big arrow is A equals int. This squiggly thing is enabled if you turn on the GADTs extension or type families extension, and this B is equal to bool. You can think of it as some sort of class. So you have class A equals B, and the instances for this class are supplied by the compiler, and they bring evidence of equality for those types. So if I have A equals int in my context, in my constraints, then I can work with it as with any other regular int. So foo equals even type checks, although even has type bool. Here but it checks because DHC knows that A equals to int and it can unify them, and it knows that B equals to bool, so it can unify the results as well. And when it comes to GADTs, they are always desugared to existential quantification if needed, and equality constraints if needed. I say if needed because GADTs are indeed generalized abstract algebraic data types, meaning that they cover the same space as regular algebraic data types, but they support more features. And those more features, they are exactly equivalent to equality constraints and universal quantification. So let's take a look at an example. I can define the maybe data type as a GADT if I want. So I'll say that there is the nothing constructor of type role A, maybe A, and there is the just constructor of type for all A to maybe A. And this is exactly equivalent to the more conventional definition like this. I've just written the universal quantification explicitly, and I have written out. Okay, so the suggestion is to insert a page break and go to the next page instead of erasing everything. All right, I like this suggestion, so let me copy that, undo all deletions. Page break, Control V. So here is our JDTs. Hangouts chat is very inconvenient for me to read with my current setup, but I will try. Okay, so now I can read the Hangouts chat. And with JDTs, the additional power that we have is that we are writing the types of each constructor explicitly, so we get the ability to write something like that. Let's say I'm defining a data type foo, and it has a type parameter a, and it can be either foo of int or foo of bool. And what happened here is that I instantiated this a parameter to so it's foo I or foo b to either int or bool, and the sort of code that I can write with this definition is this: take foo a, then I take a, and then I'll return a string, and this code here will, in case of foo int, I have an int, and I can show it, and in case of a bool, I can say if b then true, else false, something like that. So that's not quite correct. So this will be foo, this will be a of input, and I case foo of so case it's taken foo function, foo function, and here it's a and a again. So what happened here is that by pattern matching on foo, I learned what a is, and I hear someone with a very bad connection say something over Hangout, and I'd prefer this person to turn off their microphone. Rinat? All right, so to better understand what's happening in foo function, we need to think about the desugaring that foo undertakes. If I rewrite it using quality constraints explicitly, what I will have is that foo A is either foo I, where we know that A equals to int, or it's foo B, where we know that A equals to bool. And this constraint, it's like data stored inside of the constructor, meaning that when we pattern match on this constructor, this data becomes available to us. And in foo function, when I pattern match on foo I, GHC obtains this A equals to int constraint it gets into scope, and then it knows that this type variable that I have just selected, that this type variable is equal to int. I mean this type variable, so value of this type is equal to, it has type int, and I can apply show here. So this show, it's working at the int type. Here, the same thing happens. Now I know that the A that was passed to foo function, it is of type A, which is equal to bool, and I can work with it as with any other boolean. I can apply if to it. So examples of invocations of foo is foo function foo I5. This will give me string 5, or foo function foo B true. This will give me true. And this might start to look like dependent types. What we have here is that depending on the first value, the type of the second value changes. And it's not a coincidence. It is how we fake dependent types in Haskell using GADTs. But we're not going to go into too much detail today about it. Let's just consider another example of what we can do with GADTs like that. We can do, for instance, data type called sum, and it will have two type parameters, sum constraint C and sum functor F, and its constructor, what it will do, it will say, let's consider some type A, and the constraint C holds for this type A, and we store something of type FA, and this will give us some CF. What it uses here is existential quantification. You can notice that I have brought A into scope of the constructor, but it is not reflected in the type signature sum CF. So the function that gets sum as input, it will not know what A is, because the constructor comes on its own terms. It says, there is some A, but I'm not telling you what A it is. However, what it is telling us is that the constraint C holds for this A, and that we have a field of type FA stored here. So, for example, I can call makesum just unit of type sum peak maybe. What this contrived example shows is that when I call this data constructor, right, with a field of type FA, where F is maybe and A is unit, note that this unit is not reflected in the type signature, but what is also invisibly stored here, something that we cannot see, I will write it in curly braces. Here is the egg instance for unit. And when we pattern match on this sum in a function foo, what we get is, okay, let it be bool. What we get is maybe of some type A, so it's maybe A. And we know nothing about this A except that it has an EQ instance. How do we know that it has an EQ instance? Because it was passed to us as an invisible parameter stored inside these data constructors. So here we have EQA. And what I can do is when I pattern match in case MA of nothing, let's say this will be true, and if it's, oh, okay, it will be false. And if it's just A, the only thing I can do here with this A is to compare it to itself, because there is nothing else of the same type in scope, and the only operation I have available is equivalence. So I will write A equals to A. This is, of course, equal true if the instance of a Q is same. For unit, it is. So when I call to make some just unit, I will get this as a true result. All right, so the desugaring of sum using existential quantification looks like this. It's data sum CF for all A, CA, make sum FA. This is equivalent to the GADT that we wrote above, but it is written without the GADT syntax. So all that GADT is bringing to scope is more syntax. We can write the same data types without the GADT's extension. Using here, we are using existential quantification. And in case of foo, I have not shown it, but we could also have written it like this. So it will be data foo equals for all. Okay, it's E equals int foo I, or A equals bool foo B. And so there is nothing specific to GADTs here in the examples above. They desugar to definitions that use type equalities and existential quantification. And existential quantification is when something is not reflected in the type signature. Equality constraints are stored inside those constructors and become available when we pattern match on them. So this was probably a lot of information, and although I have been repeating myself, I have probably missed some key parts of the explanation. So I want to answer a couple of questions before we move on to the next topic. Does anyone have questions? Because I am sure that something is not clear in these absolutely contrived examples. Maybe some syntax is not clear, something that I wrote doesn't make sense as Haskell code, maybe some semantics that I wrote, you do not understand why this code is supposed to work. Are there questions like that?
Can you hear me?
Yes.
So the question is that I kind of have, like, it's not clear what's the point of sum. Like you demonstrated, but there's no clear like use case. Can you provide one?
All right, so in case of sum, the reason I use this example is that this is actually a data type that I use in Neat, the extensible language for Ariadne, and the way I use it there is that I have, let me just take a look at the code so I don't lie to you. The repository is probably visible to all Siracle employees, but I'm not sure about that. So here I have an example of code that I'm going to copy, and it uses sum. And what this code is saying is that we have a list of elements, and these elements are represented as sum. And for each of these elements, we know that there is an instance of class LM, which I'm going to cover later, and those elements are wrapped in a data constructor called command proc components, meaning that when I recurse on a list of these components, for each element, I have this constraint available for me. Probably a way simpler example would be something like this. Let's say I have a list of elements x's. All of them are sum values, and for these values, what I know is, let's say that so each of the elements will satisfy the constraint. Which class provides two integer? Is it integral? Yes, it is integral. So for each element, I know that it is integral, and let's say they're wrapped in maybe. And I can create this list like this. So the first element will be nothing. Let's say the second list will be just 5 of int. The third element will be just 5 of integer. And notice that int and integer are different types. maybe a better example would be if instead of integral I used okay, so to rational the real class, and the first element will be int, and the second element 5.9 will be double. So it's a list of types. It's a list of elements of different types. But when I want to process this list, I don't need to know that those types are the same, because all I need to know that they have the constraint real provided for them. So I can write a function f which will take a list of such a type and give me a rational f of an empty list will give me 0. So it's basically sum. Nothing is some x will be 2 rational x plus sum of x's, and this sum, it will work for any type, for a list of elements of any type that has the real constraint. And this might be valuable when those elements come from different sources. So you have a list of ints, a list of doubles, a list of rationals, a list of floats, and let's say you want to concatenate them, and you cannot concatenate them just like they are, but if you wrap each element in sum map sum just here, so this will be some list x's, this is y's, this is this, and this is, I've run out of letters, so it's q's. And these things now can be concatenated and processed as a single entity, a single list. So, okay, I have questions in Slack. Can you give precise definitions of the words existential and universal? So I will try. Not give you precise definitions in English, but I have given you a pretty precise formal definition, which is that universal quantification is a function and existential quantification is a tuple, meaning that when you have for all a blah blah blah, it's like a function that will take the type A and adapt to it. The result of this construction is valid for any value of A, for all values of A. And when you have exists A something, then this construction, it already has some A inside of it, and there exists some A inside of this construction, like an element of a tuple, and it is telling you which type A it is. So the second question is exists an actual keyword in Haskell? No, it is not an actual keyword in Haskell, and the reason that we are calling this for all thing existential quantification, the reason we are calling it existential, although it doesn't even mention the exist keyword, is that existential quantification can be encoded as universal quantification the same way that tuples can be encoded as functions. You probably know that if I have a tuple AB, then I can encode it as a function from A and B to R to R. This is continuation passing style for the same thing. And that's what's going on with these for alls and exists. When we don't mention the type variable in the type signature, it's the way that GHC treats it is that it puts the value of this type variable conceptually, not at runtime, but conceptually, as another field into the data, into the value constructor of this data type. And this is like when we are constructing something existentially quantified, we are providing the value. So I'll copy the definition of B here, which is our example of an existentially quantified data type. It is like a tuple. So I can, when I construct it, put two elements into it. I say I'll put int as A, and I will put as the type A, and I will put 5 as the value of this type. So I have put two things into it, and now it stores them like a tuple of two elements. And when I pattern match on it, I too have two elements provided to me, the type of this thing and the value of this thing. The difference being that since the type is erased at runtime, I cannot do anything with it. But if I was going to give this thing as sort of a type signature, but not really, I would say that it exists some. So this n inside, what type does it have? It has type exists something. There exists some type A for which type we have a value of. It's like a tuple. Okay, so the third question is, you mentioned thinking about tuples and functions where you were talking about existential types, but never explained what you meant. Can you elaborate on that? I think I have accidentally done just that. So the next topic I was going to cover is the REFL constructor, and it's defined. Oh my, I deleted all code. I shouldn't have. I brought it back, and I'm going to create a new page. Right, so bad habits die hard. The REFL constructor is defined in the base libraries like this, but it might be very confusing as to not quite like this, like this, but it may be very confusing as to what is happening here. So I'm going to desugar that manually. I'll write it like this. We have a type constructor which is symbolic, but can be written in prefix form we take two type variables, universally quantified, and we say that they are equal, and this gives us REFL. Or the middle ground between these definitions is like, can be written like this. So if you understand any of the three, you understand all of the three. They are equivalent. The one I prefer is the last one. What it makes very clear is that we have a constructor REFL that takes an equality constraint as input. So when we pattern match on it, we get this equality constraint back. And as an example, I'm going to write a function with REFL, and it will say that given a proof that A equals B, and given A and given B, I will give you bool. Okay, so I can put now an EQ constraint on any of those two. And by taking REFL, I can just return the equality operation. So how does DHC know how to type check this equality operator if it was given to different types, A and B? We cannot compare two different types in Haskell. We can only compare the same type, and only if it has an EQ constraint. But what's going on here? We are comparing A with B, and B doesn't have an EQ constraint in scope. So what's happening is that once I pattern match on REFL, an invisible field inside the REFL constructor is now available to me. This invisible field contains this equality constraint, and after the equality sign here, DHC now knows that A equals B, and indeed, if we have an equality constraint for A and B is the same as A, then we have an equality constraint for both of them. It's the same thing, and we can compare them because they are the same type. If I call wfoo REFL true, this will give me true, of course. This will give me false. And if I try to do this will give me a type error. Why? Because to construct REFL here, to create this value, I need to prove to GHC that A equals to B, because it needs this equality constraint to put it into the REFL constructor. It's like a field stored in this constructor, but here GHC will try to find this equality. It will try to say that the types of true and unit are the same, but of course bool and unit are not the same. It will fail to create this, to find this equality constraint, so it will fail to construct REFL. And the reason, so at this point you might see that equality constraints and REFL are very similar. REFL is just a wrapper around the equality constraint. Why would we might want to use it? Well, the reason is that an equality constraint is a constraint. It will take a type, another type, and give you a constraint. But the REFL constructor is type. I don't know how to pronounce it. The equality constraint. Okay, this will be the equality type. It has a different kind. It is type to type to type, and the fact that it ends in type means that we can store it inside our data, like inside a tuple. We can have a tuple where we say that A equals to B, and there is an A. So this is valid Haskell, while this is not valid Haskell. Okay, so I'll change it to int probably. So this is valid Haskell, and value of this thing, it can be something like this. It's REFL5, while this is not valid Haskell because I cannot put a constraint into data as a field, unfortunately. Of course, I would like to, but that's not a fundamental limitation. That's a limitation of Haskell that we cannot. So we are forced to create wrappers like this. It's redundant, but we need it. Now let's move on to the next point.
I have a question.
Okay.
Why not use dict instead as a more generalized version?
We can use dict instead, but the problem will be partial application, meaning that I can write dict. So dict, what is dict? Dict is defined like this. For any constraint C, I can construct a dictionary of this constraint, meaning that I can create a tuple like this, dict q of a, and this tuple will contain proof that A has an equality constraint. This proof is just a value of dict, which I can pattern match on and get this constraint in scope. The same thing is happening with the REFL here. This is just a wrapper around a constraint. And with sum, when we were defining sum, it was containing a constraint inside of it as a field. So dict is basically a wrapper around a field which contains some dictionary, class dictionary. That's why it's called dict. But while I can write something like this, I cannot write something like this with dict. So here, this is a partially applied equality type, meaning that its kind is type to type. But I cannot do the same with dict. It would require me to write something like this, and that would hopefully have the kind I need. But we don't have composition on type level. We have it on term level, composition of functions, but not on type level. So we are forced to create more wrappers than we normally need. Just more boilerplate in Haskell, yay! And whoever thought that Haskell is an elegant language without boilerplate must be very disappointed now. We have entire key hierarchies of types of pure boilerplate in our base libraries. All right, so let's move on. Product types, which are pairs, units, flat tuples, nested tuples, list, h-lists, and so on. The reason, okay, I'm trying to delete everything again, and you have probably seen it by seeing that I have selected everything, next time it's a good idea to stop me because I'm doing it out of habit. So product types. Product types are called this way in case someone didn't know, because the amount of elements of a product type is a product of the amounts of elements of each component. Meaning, if I have type bool, it has 2 elements, and if I have type color code, like RGB, 3 elements, then pair of bool color code, its size is unsurprisingly 2 times 3. Why? Because we have true red, true green, true blue, and the same thing for false. Okay, so Google Docs apparently is too stupid to understand that when I select something and I use find and replace, it needs to find and replace only in the selection. So I'll do it manually, all right. So here are 6 values, and that's the logic behind it. That's why those are called product types. And as products, as we know from numbers, from our experience with numbers, if we multiply something by 1, it stays the same. And this holds for algebraic data types, for product types, because we can define a data type with a single value, data unit, make u. It has a single value u, it's 1. And when we have a tuple with unit as one of its component, it's basically the same thing as the other component because it has the same amount of values. Of course, the disclaimer here is that I'm ignoring bottoms. In Haskell, there are values that inhabit every type, which are looping computations and computations that throw exceptions. But if we ignore all that, we get a nice algebra of types where multiplying by 1 is an identity operation. And we can define a product of 0 types, its unit, because the intuition for this is that if you take the term level function product from Prelude that works basically on ints, if you call product of 0, it will give you 1, because when you multiply, if you call a product of an empty list, I mean, it will give you 1. So that's because when you multiply 0 types, you get the identity element, you get 1. And that's the same thing happening here. A product of 0 types is unit. Then a product of 1 type is identity, because it's not multiplied by anything really, it's just identity. And product of 2 types is a pair. A product of 3 types is triple, and so on. And the unfortunate bit here is that GHC defines separate data types for each length of the tuple, and it stops at 62 for no reason at all. 62 is pretty arbitrary. In some very old compiler version, 63 used to crash it, but now it doesn't. So we are stuck with this 62, and there is no reason why. And another problem with this is that it's very difficult to work with these tuples generically. So let's say I want to take some tuple and get its length. I will create a class called length, and it will have a method L, which will take A and give me its length. And for unit, the length is 0. As we discussed, unit is a product of 0 types. For identity, length is 1. For a pair, the length is 2. For a triple, it's 3. And so on. And I could go on forever. Actually, not forever, up to 62, but conceptually forever. And this is very sad, I think, because this means that anytime we want to work with some product of types of unspecified length, we need to create instances for each possible length. And this may result in incredible amounts of boilerplate. So what we should learn from is lists. Lists teach us that we can represent things of arbitrary length using two constructors, cons and nil. So if I define only two product types, nil and cons, which are just unit and pair with different names, you should recognize them. It's one, it's multiplication. I'm actually going to use something infix here. So I can represent any product that I used to represent in a flat manner using cons and nil. So instead of int bool char, I can write int, it's infix r, right? So int bool char nil, of course, the last element. And if I want to write a term of this type, I will, of course, write 5 cons true. Let's rename this also. 5 true x, y, nil. So it's like a list. It's very similar to a list, and but the difference is that every element is reflected in the type signature, so we can have elements of different types. We cannot create a list of an int, a bool, 2 characters. We can only create list of ints, list of bools, list of chars, lists of sums, like I defined before, but all elements have the same unified type. Here we have different types, so it's I don't know how to pronounce it correctly, so correct me if I'm wrong, but I will call those heterogeneous lists. And for heterogeneous lists, we can define a length class which will only need 2 instances. So an instance of length for nil is 0, and an instance for length for cons, a cons x's, will be equal to 1 plus the length x's. And in the instance, I need a constraint length for x's. So it's an inductive definition, meaning that we define a base case, we define a single step of reasoning, and we get length defined for all possible lengths. Okay, I have a question in the channel important. Can you type out the term you couldn't pronounce? Okay, heterogeneous. I don't know. Anyway, the value that this approach brings to the table is this sort of inductive reasoning where we can define operations generically using a finite amount of instances. But a problem with this is that nothing enforces maintaining this structure, meaning that I can forget in foo prime, I can forget the nil in the end. So no nil, this structure will type check. It's a valid value in Haskell, but from our point of view as heterogeneous lists, it's a broken structure. And that's because the nil, the length definition will not work for it. It will treat char as the last element, and it will not find a length instance for it. So this clause, this inductive clause, it will fail. And that said, I don't want that to happen. So, and another thing that I don't like is that for every operation like length, I have to define a new class. It's not the way I'm used to writing a Haskell, a class for everything. I'm used to writing a function for everything. Why should I create a class? And this brings us to the GADT-based definition of heterogeneous lists, which looks like this. It will take a list of type x's, and it's either nil, which is a list of x's where x's has an empty list. So I'm doing some desugaring here for clarity, and I have the cons constructor, which is 2, a heterogeneous list, but it also contains two fields. It contains some element A, some other heterogeneous lists A's, and we know that x's is A and A's. So what's going on here? This basically brings those two data types, nil and cons, into a single GADT. And it also uses data type promotion. Is anyone in this call unfamiliar with data type promotion because I've just realized that I haven't covered that. It's quick to cover, but I want to confirm that that at least one person needs it.
You mean data kinds?
Yes, data kinds, the data kinds extension. All right, so the data kinds extension makes the grammar for kinds in Haskell way bigger. Yes, let's move to global instead of important because we are spamming this channel. Anyway, data kinds. The default grammar for kinds in Haskell looks like this. Kind k is either star or it's some kind to some other kind. What does this mean? This means that type int has kind star and it has values that inhabit it. Values, only types of kind star have values that inhabit it. So I can have phi of type int of kind star, or I can have true of kind bool of kind star. But I cannot have a value of type maybe, which has kind star to star, because it's not a fully formed type. It's a type constructor that needs to take another type as input to give you a type as output. So that's how kinds work in Haskell by default. If we enable constraint kinds, the constraint kind extension, then our grammar is, so this is the default. So if we enable the constraint kinds, our grammar is slightly bigger. It has a new kind, constraint. We can say things like EQ is a type, so there is nothing that inhabits it, but it is a type which has kind from star to constraint. And if you give it an argument like qint, it is actually a constraint, and a constraint is a thing that can go to the left of the fat arrow. So I can write qint blah blah blah. And this constraint kind, it is inhabited by invisible values, class dictionaries. So when I have a qint, it is actually a tuple in memory, and this tuple contains two functions. The first function is int to int bool. This is the equality function, and the second is int to bool. This is the inequality function. So I should have written things like this. So it's basically a record with two values. And that's how constraint kinds work. But we can extend the kind grammar further by using data kinds. And now the grammar is of kind it's either star, the kind of inhabited types, or it's constraint, the kind of things that go to the left of the big arrow, or it's function on kinds, of course, or it's a promotable type. And promotable types are any algebraic data types without fancy features. So booleans are an example of that, and H-lists are not an example of that, because H-lists use fancy features. They use type equalities stored in them, and sum is not an example, and B from the beginning of the lecture is not an example because it uses existential quantification. But anything that doesn't use anything fancy, it's promotable. So we will have bool here, and if I define data foo A, B, C, we will have foo here. We will have lists of kinds here because lists are defined without anything fancy. They are just either nil or cons. It's not fancy. And we have other things, but the main struggle right now with in GHC is making more types promotable. You may have heard of the type in type extension introduced recently by Richard Eisenberg. So what this extension does is that it allows more types to be promoted. Now, if you turn on type and type, types that contain equality proof inside of them, like H-list with an equality proof inside of it, it can be promoted. So it will actually join the grammar of kinds, but still not all types can be promoted. Built-in types like char or like int, they cannot be promoted. Natural numbers defined like this, no problem. But integers as defined in GHC, they cannot be promoted because they use a C library to, so for integer, we have a C library GMP used to implement it. And for ints, they are actually GHC built-in, so not promotable either. But instead of them, we have other kinds, net and symbol, which are only valid as kinds, but as types they are uninhabited. So that's a different topic. I shouldn't try to explain it here, but the way data kinds work is that now we have lists in our kind grammar, and we can have H lists defined above like that. They have the H list type constructor has the following kind. From a list of types, it gives you a type. So H list of an empty list of types, it's kinda sorta equivalent to unit because it has just one value, nil, and unit has just one value, unit. H list of a single element is sort of equivalent to this element because it's a product of one element, and H list of two elements is sort of like a pair. An H list of three elements is sort of like a triple, and so on. But of course, the difference here is that now our definition is inductive. we have two constructors and we can pattern match on them, and we can define operations on them that work for any length of an H list. So first, some examples of constructing an H list. An H list of char, bool, int can be constructed like this. So here I need a fixity declaration. It can be constructed like this: a character, then a boolean, then an integer, then a boolean, then an integer. This should be, if I put parentheses here, valid Haskell. And it's a hybrid between tuples and lists. It's like tuples in the sense that it has different elements, and it's like a list in the sense that it has a list-like structure of cons and nil. And this list-like structure allows us to define generic operations on it without classes and without instances for each possible length. I can write h length, which will take h list of some unknown sequence of elements. I do not assume anything about access, but I will give an int. Okay, someone is asking for a break. When I'm done explaining H lists, we will take a 10-minute break, and the rest of the topic, let me see how I'm doing on time. We have some types to cover: computing constraints with type families, data families, and parameterization of H lists and units. So far, the lecture has taken 1.5 hours, so I'm doing just fine with the time. H length of nil will give us 0, and H length of something cons access equals 1 plus H length of access. And this mirrors the traditional definition of length, except it works for H lists, which are more like tuples, meaning we are treating tuples like lists, which is amazing, I think. So just to make sure we understand why these type checks, when I pattern match on nil, I have a proof brought into scope that access equals an empty list of types. I'm not using this proof to return an int, but I have it. Another question is what those primes in types are. So you can see that instead of writing an empty list here, I wrote prime empty list. The reason I wrote it like this is that GHC cannot disambiguate between a promoted list constructor and the list type itself, because if I were to define lists with Haskell syntax, I would define them like this. Right, so a list of A's is either A cons list of A's or nil, but when we promote it, how do we distinguish between a list of int and which can contain values like 1, 2, 3, and a type level list that has one element int and it's not actually an inhabited type? So the syntax makes it very confusing, but if I just redefine the list like this, if I write that a list of A's is either cons A or nil, then this becomes pretty clear because here we can see the difference between list of ints and cons int nil. So this is Haskell syntax for int, and this is Haskell syntax for prime. I got confused. The Haskell syntax for list of int is int in square brackets, and Haskell syntax for cons int nil on type level is prime int in square brackets. And back to age length, the way it works is that when we pattern match on nil, we get a proof in scope that access is an empty type level list. I'm not using this proof to return 0, but I have this proof in scope just in case. I might have used it for something else, but here I'm not using it, and I just return 0. And here, something more interesting happens is that I pattern match on this cons constructor, and I get a proof in scope that this type level list access is actually a list of at least one element. It at least has A, and it also has the rest of the elements A's, which are stored as a second component, HList, and I call HLength on it, which will compute the length of the tail of the list, despite its elements being of different types. So we are not expecting the elements themselves, but in this definition, we know nothing about them. We could not actually do anything with an element of this list if we wanted to, because we have proofs that the list itself has certain structure, that it's either nil, we pattern match on it here, yeah, we know it's an empty list, it's another option is that it's cons, we pattern match on it, we know it, it's not an empty list, but we don't know anything about the elements. And now I'm going to make a 10-minute break, and we will, after the break, learn how to assume things about elements in heterogeneous lists, how to constrain them in ways that allow us to manipulate them. So I have 3 minutes before the break, so prepare your questions, and after the break, I will have answers prepared. All right, I'll actually just mute the mic and I will be still here, but anyone who needs a break can take a break. I'm going to be back in 13 minutes. It was 13 minutes, not 30.